Hello everyone. Now we start with the second chapter, which is about the axial loading and the related the province in the analysis and calculations of the stress. And we see the outlines here for these chapters. We're going to spend about per the schedule about 10 days in your self-study about the topics. In first one, in the chapter 1 we have learned how to calculate the stress. Beginning with the second chapters, we're going to introduce how to measure the deformation, and from the deformations we're going to introduce a term that called the strain. Okay, in particular, the second chapter is going to focus on the axial loading, which means consider this is a bar, and the loading is in parallel to the, I would say, the longitudinal direction of the bar, like this. So basically, this case is for tensile loading. This is for compressive loading. And the tensile loading going to stretch, which means we expect the bar going to be longer after loading. Compressive loading going to shorten. That means deformation going to be negative. That means it's shorter than his original undeformed length. Then the final portions of these chapters is going to exercise a very important application we call the indeterminate province. And those provinces usually happen in over-constrained static province, but that also will appear in other type of the province, and I'm going to illustrate later on in the slides. And in this province, basically the definition is this: the number of the reactions, which means usually appear as the unknown in the equilibrium equations. Okay, the number of the unknowns in the equilibrium equations are larger than the number of the equilibrium equations itself. So, which means, for example, if you would have two equilibrium equations, however, you have three unknowns, basically here we wouldn't be able to completely solve for those three unknowns out of two equations. So these provinces are defined as the indeterminate province, indeterminate of the unknowns simply based upon the equilibrium equations here. Those provinces are very important, actually going to occupy quite a bit lectures hours in the second chapters, and those provinces will appear again and again in the following chapters. So we see, okay, so the first portions out of 10 is to define the strain. The strain can be visualized as by first identify what is the deformation. Look at this province, this BC before any loading applied, and that is undeformed, or we call the original length. When the loading applied and reach static equilibrium, for this case is tensile loading. BC going to be stretched a little bit, and the difference between the deformed and original length is called the delta. That is what we define as the deformation. Okay, and similar, we consider another. This is bigger. Okay, a bigger shaft, and under any magnitude, say here 2p. So again, for determining the deformation, we simply compare the lengths, the dimensions after and with the original one. So here is delta. Okay, very straightforward. And for this case, that deformation is 2 delta. Okay, so with the deformations be determined, then we can introduce the strain. Basically, strain we using the notation epsilon, and epsilon strain as defined by the deformations divided by the original length or original dimensions of the material model. So for this case, the deformation is delta here. And then original length we measure is L. So basically that determined by strength. And strength has no unit. For example, this is in length unit, this is in length unit, basically is no unit here. And we can look at this example here. So the strength for this example is deformation, that is delta, divided by original length is L. Okay, simply calculate it like this. And how about for this? For this one, the deformation is 2 delta, and then the original length is 2L. So basically this delta over L. So for this numeric example, you can see strength equal to this and strength equal to this. So basically the strength in this system and in this material model, in that material model, based upon our calculation, they have the same strength. Okay. Now we can exercise our stress calculation, and assuming this has a cross-sectional area A, so stress is magnitude of P divided by A, P over A. And assuming this one has the cross-sectional area 2A, so the stress is 2P divided by area 2A, P over A. Okay. So now for this case, assuming this one has the cross-sectional area A, so the stress simply is magnitude, which is P divided by A, P over A. Okay, so that is a calculation like this one.